So, what we are going to do today is pipe flow. Okay. In terms of calculations, okay, the calculations are very simple, straightforward. You would have also probably seen it, but the concepts that get introduced, okay, during this calculation, they are very important, okay, and that's because it's the same concept that we will keep talking again and again in various contexts throughout the course and probably throughout the your degree here. Okay, so that's the importance of pipe flow. So, so the calculations essentially are very similar to what we did in the 2D channel. Okay, you basically want to find out how you can describe flow in a cylindrical pipe. Okay, so when I say pipe flow, it could be actually any cross section. And when you go to a real system, okay, for example, you go to an industry, you need not always find a cylindrical pipe. You might find a square pipe, rectangular pipe, and so on. In fact, you could ask the question, what is the pipe that I should choose when I have an application? When I want to, let's say, transport things from one point to another, let's say crude oil or some chemical, what should be the shape that you should be choosing? At the moment you don't know, and we probably will not talk much about it, but we will see what various shapes would mean. That will come at a later part, but this forms a basic example. So, you have a pipe . Okay, and there is a fluid that's going in and coming out, and in order to attain that, what you can do is you can apply a pressure gradient. You will apply a pressure P plus delta P on this side, and this side can be pressure, and if as long as delta P is greater than 0, fluid is going to go from one side to another. Okay, and again we are going to look at fully developed flow. Yeah, so as we said that day, when the moment the fluid enters here, there will be an entrance region, okay, where the flow is developing. That means if I am going along this axis, along the pipe axis, I would see that at every point the flow is changing, but beyond a point flow does not change, right, and that is what we termed as fully developed flow. So, fully developed flow is that flow which is coming after the entrance length. Okay, and we are basically dealing with fully developed flow because entrance length may not be so long, while we might be talking about pipes which are like kilometers long. Then we don't really care what happens at the initial portion. So, let us as well neglect that initial portion and work only with the fully developed flow for the time being. Okay, and let us use now which coordinate system would we choose for this problem? Why would we choose cylindrical coordinate system? Because it is a cylinder. So, let us say now I want to solve flow in that. Cartesian? Okay, so what decides what, how should we choose the coordinate system? We will see that, okay, I will answer the question as we go along. So, let us choose the cylindrical coordinate system. We will say that that's our z axis, that's our r, and then theta is going to be perpendicular to the plane and around the z axis. We can so what is the first thing to do? We will write down the governing equations, which is continuity and momentum equation. We will start with the continuity equation and we will make few more assumptions. So, we derived continuity equation yesterday. What was that? I hope you will tell. Are you going to tell? No, I am going to write it down in cylindrical coordinate system. This one what you see on the screen, okay. So that's the continuity equation. So you have ur, u theta, u z. So these are the three components of velocity as we described yesterday. So we have fluid which is going from one side of the pipe to the other, okay. So the component of velocity that we are interested in is u z, okay. So we really want to know what is u z, and if you remember what we did in the 2D channel, okay, what was the component of velocity that we had? We had a component which is parallel to the channel axis. We did not have a component that is perpendicular to it, okay. So here also it's unlikely that we will have a ur, okay. Ur is likely to be 0, and we will right now assume that ur is indeed 0, okay. You can question that assumption, but at a later point. So let's assume that ur is equal to 0. We will also assume that u theta is equal to 0, okay. Now assuming u theta equal to 0 is much more sensible, because what is u theta? U theta is essentially, so let's look at a cross section of this pipe. Let's say that's a cross section, okay. So flow is coming from behind the screen through the screen to outside, and let's say you have an x, you have a y, and that's what you define as theta, right? So then I could say that, okay, my u theta, which will come out to be some function of theta, if I say, I could also draw my coordinate system in that fashion, right? That's also an acceptable coordinate system, in which I would define my theta that way, right? So the theta that I would have defined in my original coordinate system and the theta that I will define in my new coordinate system would have been different, okay. So it's unlikely that therefore there can be u theta dependence, because you won't be able to find out a mathematical expression that will do this, okay. That any coordinate that you choose, whether you choose this x o, y o, x n, y n, whatever coordinate system you choose, there will not be any mathematical function that's going to tell you that you're going to get the same number, okay. So it's unlikely that u theta will be coming out to it will come out as a non-zero quantity. That's one reason to a priori assume that I can actually start by saying that u theta is 0. Is that clear? Okay. So even if it's not, it's okay. I mean, let's just assume that u theta is equal to 0. We will also assume that del by del theta of anything is equal to 0. What is meant by that? As I go in the theta direction, so as I am going in this direction, again I am assuming that there is nothing that is changing, okay. So that's, so imagine, so you exactly have a circular pipe, okay. So why should any point be different than any other point? That's the idea, okay. So therefore you are going to assume that del by del theta of anything is also going to be 0. So these two assumptions are known as axisymmetric. So we are essentially assuming that flow is axisymmetric. So flow is axisymmetric. So basically meaning that around the axis, around the z axis, okay, flow is symmetric. That's the assumption that we have gone in, or we have taken, and we are only looking for the uz component. The uz component is typically called the axial velocity. That's velocity along the axis. Yeah. You can, so you can't assume both of them to be 0 as a consequence of fully developed flow. You can take one of them and the other can be shown that fully developed flow is consistent with this approximation. So let me just show you. So let's say if you take ur is equal to 0, u theta equal to 0, the continuity equation says that's gone, and only this is left, which is what our fully developed flow is. Okay, so it's so only thing I am saying is that fully developed flow and these two assumptions are consistent. Okay. Now on the other hand, if you wanted to start by saying that, okay, I have fully developed flow, so dou u z by dou z is equal to 0. Then suppose you started with continuity equation and you could have said, okay, dou uz by dou z is equal to 0. So this I am going to put to 0. Then you have to either assume u r equal to 0 or u theta equal to 0 to get the other is equal to 0. So if I say u r is equal to 0, I will push that out. Then I have dou u theta by dou theta, which will come out to be a constant. Okay, but it will be 0 at the wall and therefore it will be 0 everywhere. What is that? Axisymmetric flow is a fully developed flow. Accelerating flow is not a fully developed flow because it's changing in space. So by definition, this is our definition of fully developed flow. If u z is changing with z, then it's not called fully developed flow. Okay. For example, the flow that's coming from here to here, things are changing in z direction. So you can say the flow is actually speeding up or slowing down. Okay, that speeding up is in space. As well, it could be in time also, but it's accelerating in space. So wherever it is accelerating or decelerating, you will not call it a fully developed. It's a developing flow against a fully developed flow. Okay. All right. So those are the assumptions. Now we can just go ahead, write down our force balances, throw out all the unnecessary terms, and then see what is left out. Okay. Any doubts otherwise on this? So just one thing. So we have dou uz by dou z is equal to 0. That means uz is a function of r and theta, but because of the assumption of axisymmetry, by definition things are not dependent on theta. So we have just uz as a function of r. Just the way in the other problem we had a velocity nor parallel to the channel is just a function of perpendicular direction. So similarly here velocity is along the pipe axis and it will vary only in the radial direction, and that's what we are going to derive. So let me write down the equations. R momentum equation So now it should not be surprising to you why we get all these extra terms, right? So this right hand side is actually del square of u, right? It's second derivative of u. So we already saw what divergence did. It's just second derivative. So there are many more differentiations. All those unit vectors are going to contribute to many things. Okay, that's why you get all these extra terms here and some of the extra terms there. All right, okay. So that's how the momentum conservation equations look like in the cylindrical coordinate system. And what is the best way to start with? We can start by looking at the r momentum equation and the theta momentum equation and throw away all the unnecessary terms. So, Asha Ramanujam, yeah. So what is left out in the first equation? Can you tell? So that goes, that goes, that goes. This, all of them go, only that remains, and therefore it tells you that P is not a function of R. Okay. Yes, yeah, we are still going to look at horizontal pipe. P is not a function of R. Mani Chandana? Yeah, so what is left out in the theta momentum equation? Left hand side is 0. Dou u r by dou theta, it's 0. So all of them went away, and therefore you are finding that P is also not a function of theta, and P is only a function of Z. Okay, that's going to be nothing but the pressure force that you have applied. Okay, pressure is high on one side and pressure is low on the other side. It's just exactly that. So P is only a function of Z. Khyadi Mishra. Khyadi Mishra, what is left in the Z momentum equation? Let's start one by one. How about dou u Z by dou t? It's 0. How about u dot grad u Z? So you can see this is what the equation is going to be, okay? U dot grad Z. U dot grad Z. So u dot grad u Z would mean u r dou u Z by dou r plus 1 by r u theta dou u Z by dou theta plus dou u Z divided by dou Z. How about u r dou u Z by dou r? Is that 0 or non-zero? U r is 0, so it's not there. U theta is 0 and dou by dou theta is also 0, so that's not there. How about dou u Z by dou Z? That's also non-zero, okay, because it's fully developed flow. Fully developed means nothing is changing in Z direction, so that entire term goes away. Okay. Yeah, Samyukta. So how about on the right hand side, dou P by dou Z? It's non-zero, so that remains. How about del square u Z? So del square operator is that. So we can write down and see del square u Z is 1 over r del by del r of r u Z plus 1 over r square del square u Z by del theta square plus del square u Z by del Z square. How about the first term, 1 over r del by del r of r u Z? It's non-zero. How about 1 by r square del square u theta by it's 0, and del square u Z by del Z square 0. So it's only that term that's left out. So we basically find that 0 is equal to minus dou P by dou Z plus mu into 1 by r into del by del r of r u Z. That's the differential equation that we have entered up with. Correct? Any doubts? Okay, we can, so what kind of a differential equation it is Mahir. Mesiva. What kind of a difference? Is this a partial differential equation or an ordinary differential equation? That's the question. So, we said P is not a function of r and theta. So, I can write this dou P by dou Z as really dP by dZ, okay, and therefore, uz is only a function of r. So, that is again an ordinary derivative, okay. So, it is no more a partial differential equation, it is an ordinary differential equation and you know how to solve it.